Hi, this is week 31 of AP Physics, and in this week we'll be going over a lesson on electrical energy as well as power and resistors in series. For our lesson objective, students will learn how to calculate the current of a circuit when the resistors are in series. Let's go ahead and get started.
Let's begin by discussing electrical energy and power. A charge moving through a conductor has kinetic energy. This kinetic energy is quickly lost as a result of collisions between the charge carriers and fixed atoms in the conductor, causing an increase in temperature. That is how a toaster oven works, or anything that heats up. For example, the heating element in a water heater. If you have charges going through, as they collide with atoms in the conductor, they're going to go ahead and lose kinetic energy, and it will be transformed into thermal energy. As the charge moves through the battery, its potential energy also increases. As a charge moves through a resistor, collisions with the atoms reduce the electric potential energy, which increases the temperature. The charge will regain its energy once it passes through the battery at the expense of the chemical energy in the battery. So the battery goes ahead and increases the potential energy for the charge, but it does lose chemical energy along the way. Eventually that will lead to the battery losing all of its chemical energy, and we refer to the battery as being dead. Now power, whose symbol for it is P, is the rate at which energy is delivered to the resistor. So P power is equal to I, which is the current in amperes, multiplied times the potential difference, which is measured in volts. Now that also equals to the energy over time. So that is how much power it is. Now, energy over time is worth discussing a little bit. That, let's say I ask you to move a heavy object over some distance. All right, so it requires energy. Now, if you move that object very quickly over a short period of time, then you will need a lot of power. So the energy to move that object over a short period of time, because the time is in the denominator, is inversely proportional to the power. So the smaller the time, therefore the larger the amount of power needed. Vice versa, you move the same object, so it requires the same amount of energy, but you take a long time to do it. Therefore, since again they're inversely proportional, time and power, if it takes a long period of time, therefore you use less power. So the amount of energy over time gives you power. Now the equation delta V equals IR, which is the potential difference equals the current multiplied times the resistance, and power is equal to current multiplied times the potential difference, can be expressed as following. So we can go ahead and rearrange them and put them together. So we have power is equal to I squared times R, so it's the current squared multiplied times the resistance, or you can also equal them to delta V squared, the potential difference squared, divided by the resistance. Some reminders: I, of course, is current measured in amperes. Delta V is potential difference or voltage measured in volts. R is resistance measured in ohms, and P is power, and the unit for power is the watt.
Let's take a look at example 3. Here we ask, a circuit provides a maximum current of 12 amps at an operating voltage of 120 volts. In part A, they ask how many 75 watt bulbs can operate with this voltage source. Alright, so let's go ahead and take a look at part A, how many bulbs will be able to operate. So what we're going to go ahead and do is we have the current and we have the voltage. So we're going to go ahead and figure out the power, which is going to be in watts. And then we can go ahead and use that to figure out how many 75 watt bulbs we can go ahead and power. So let's begin there. So part A, power is equal to I, the current, which is 20 amps. And we're going to go ahead and multiply times the potential difference, the voltage, which is 120 volts. Alright, so we're going to go ahead and get, it's going to be 2400 watts. Alright, now if each bulb uses up 75 watts, how many bulbs can we power? So it'll look like this. It'll be 2400 watts. And for every one light bulb, it uses up 75 watts. So it will be 2400 divided by 75 watts. It's going to give us 32 bulbs that could be powered by this 120 volts and 20 ampere current. Alright, so now part B, they ask you at a cost of 12 cents per kilowatt hour, how much does it cost to operate these bulbs for 8 hours? All right, so now we're going to leave them on for 8 hours. It's costing us 12 cents per kilowatt hour. Let's go ahead and work out this problem. Now for this one, we're going to go ahead and use the formula for power is equal to energy over time. All right, so now that we have the power, we can go ahead and move the time over to figure out how much energy it would cost. All right, so energy is equal to power multiplied times time. All right, so our power is 2400 watts, and the time is going to be 8 hours. So that's going to go ahead and be 8 hours here. All right, and but wait, I want to go ahead and change it because normally it's 12 cents per kilowatt hours. So this 2400 watts, I want them in kilowatts. So I'm going to divide it by 1,000, so it is 2.4 kilowatts. So multiply 2.4 times 8. It's going to go ahead and give me 19.2 kilowatt hours. So our watts, change them to kilowatts instead of 2400. Now it's 2.4 kilowatts. Multiply times hours, so we get 19.2 kilowatt hours. All right, now every kilowatt hour costs us 12 cents. So now our next part, we're going to get our 19.2 kilowatt hours. Let's say 1 kilowatt hour is equivalent of 12 cents. So we're going to go ahead and multiply. And it gives us a value of 2.3 or $2.30 to operate these bulbs for 8 hours. All right, that is example 3. Up next, we're going to go ahead and do problem number 6. And this one says, considering how hot the parts of an incandescent light bulb get during operation, guess, so this is a guess what fraction of the energy emitted by the incandescent bulb is in the form of visible light. The answer for this problem is 10%. Again, we're just guessing, but it's about 10%. 90% of the energy is dissipated as heat. Only about 10% of the energy it's actually turned into visible light. All right, let's go ahead and move on to problem number 7. In this one, they ask you, part A, how many Christmas tree lights drawing 5 watts of power each could be run on a circuit operating at 120 volts, providing 15 amps of current? All right, so we're going to go ahead and figure out the number of the bulbs. And then after that, we'll do part B. All right, so for our bulbs, we have, again, let's figure out how much power they need. All right, so it's going to be power is equal to the current, which is 15 amps, multiplied times the potential difference, which is 120 volts. So it's going to go ahead and give us the following. 15 times 120 gives us 1800 watts. All right, now that we have that, we know that each one of those bulbs takes up 5 watts. So I'm going to get my 1800 watts. And now I'm going to go ahead and put for every one bulb, it's 5 watts. So I'm going to get 1800 divided by 5. It's going to give me 360 of these little tiny Christmas bulbs that could be illuminated with a voltage of 120 volts and a current of 15 amps. Now, part B, they ask you, find the cost to operate such a string for 24 hours a day for the Christmas season, which is 2 weeks, using the rate of 12 cents per kilowatt hour. All right, so again, we're going to go ahead and use this formula right here. So for our, how much energy is that going to be? So for part B, it's going to be the power multiplied times the time. All right, and the unit for power we're going to use is kilowatt hours. So we want to get our watts and change them to kilowatts. So we're going to get 1800 into watts divided by 1,000. So it's going to go ahead and our power rate is 1.8 kilowatts. And we're operating 24 hours a day for 2 weeks. First, let's figure out the cost per day, and then we'll multiply times 14 for the 2 weeks. So it's going to be our power multiplied times 24 hours. All right, so because we're running them 24 hours a day, It's going to go ahead and give us 43.2, and that's going to be kilowatt hours. So we have kilowatts here times hours, so it's kilowatt hours. Now, how much does it cost per kilowatt hours? It's 12 cents. So we're going to get this value, 43.2 kilowatt hours. And we're going to say, well, for every 1 kilowatt hour, we're going to go ahead and pay 12 cents. So how much money will it cost us per day? So it's going to be times 0.12. It's going to be $5.18, a little bit rounding off, per day. Alright, now the Christmas season is, according to this problem, 2 weeks long, so that's 14 days. So it will look like this. So if you have 14 days, how much would it cost me for the whole season? 1 day cost me $5.18. So it'll be 14 times 5.18. That is $72.52 to run your Christmas lights for 2 weeks, 24 hours a day. Alright, that takes care of problem number 7. In example 4, we asked the following question. An electric heater operated by applying a potential difference of 50 volts to a nichrome wire of total resistance of 8 ohms. Find the current carried by the wire as well as the power rating of the heater. Alright, so we're going to go ahead and begin by finding the current here, I. So we're going to go ahead and isolate the I. So I'm going to go ahead and divide both sides by R. So we end up for part A, which is find the current. It is I is equal to potential difference over the resistance. The potential difference is given to us. It is 50 volts. And the R is the resistance, which is 8 ohms. So our current is just simply 50 divided by 8. So we get 6.25 amps. That is our current. In part B, they said find the power rating of the heater. Alright, for that one, we will use this formula here where we have the current and we multiply times the voltage, and that's going to give us a power rating. Alright, so that's going to be I times delta V. So the I is the current, which is 6.25 amps. We're going to go ahead and multiply times the V. The voltage was given to us. It is 50 volts. So multiply times 50. That's going to go ahead and give us, we're going to round it off to 313 watts. And that is the power rating for this problem. Next, let's go ahead and take a look at problem number 8. Here it says, if the heater wire is replaced by a wire with lower resistance, is the time required to heat the water unchanged, increased, or decreased? Those are your options. Alright, so now lower resistance. Let's go ahead and go step by step on what we know. Alright, if here resistance is and current are both inversely proportional. So therefore, if we lower the resistance, what will happen to the current? That will increase the current because they are inversely proportional. So if we lower the resistance, we'll have a higher current. So what happens if we have a higher current? If we have a higher current that is directly proportional to the power, we'll have a higher amount of power. Alright, so now, next formula we're going to go ahead and use for this one is power is equal to the energy over time. And notice that power and time are inversely proportional to each other. So since we increase the power, therefore we have to decrease the time. So the answer for this one will be letter C. It would decrease the time to heat the water if we had a wire with lower resistance. Alright, let's go ahead and move along to our next problem, problem number 9. And this one says a hot water heater is rated at 4.5 times 10 to the 3 watts and operates 240 volts. Find the resistance in the heating element and the current as well. Alright, so let's get rid of these arrows and solve this problem. Alright, so we're giving here the power as well as the voltage, so we're going to go ahead and use this formula here to find for what is the current. Okay, so now we're going to go ahead and isolate the I by dividing both sides by the V, the voltage, and so we'll look like this. Current is power over the potential difference. So power, the power is 4.50 times 10 to the 3 watts, 4,500 watts, divided by 2.40 times 10 to the 2 volts. That's 240. So plug them into the calculator. We just divide 4,500 divided by 240 gives us 18.75 A for amps. That is the current. All right, now we have the current. They ask us not just figure out the current, also figure out the resistance. So in this case, we're looking for R. So we're going to get this formula and isolate the R by dividing both sides by I. So it will look like this. R is equal to the voltage over the I. All right, so the voltage was 240 volts over the I, the current, which was 18.75 amps. So 240 divided by 18.75, that gives us our answer. The resistance is 12.8 ohms. That's our answer for problem 9. In problem 10, we're asked, a voltage is applied across the ends of a nichrome heater wire having a cross-sectional area A and a length L. The same voltage is applied across the ends of a second nichrome heater wire having a cross-sectional A and a length that is 2L, so twice as long. Which wire gets hotter? Is it the shorter wire or the longer wire? Alright, so let's go ahead and take a look at this using these formulas. So let's talk about the second wire. We're doubling the length. So here's the formula for resistance, resistivity times length over the area. If we increase the length, notice that that is proportional to the resistance, so that will increase the resistance. And if we increase the resistance, that is inversely proportional to the power, so that will decrease the power. The longer it gets, the less power we'll have. And if we decrease the power, that will decrease the energy because they are directly proportional. So if we're decreasing the energy, it's going to take longer to heat because it has less energy. So therefore, the longer wire will have less energy, so therefore less ability to heat. So therefore the question was, which wire gets hotter? That's going to be the shorter wire. The longer wire will have less energy, so therefore the shorter wire will have more energy, so therefore it can get hotter. Alright, let's go ahead and move along to problem number 11. And this one they ask you, for the two resistors, rank the currents at point A through F from largest to smallest. So here we have the diagram. Here's A, B, C, D, E, F. So between A and B, that will definitely be the highest right here, current, with the battery next to it. So it's the answer to the A or B. Notice they have A, B first. So we can go ahead and cross out letter C. Next, let's go ahead and take a look at resistor A and resistor B. Notice that the power is much higher here for 60 watts. So therefore, it must have a higher current. All right, so therefore, CD would be next, and then last one would be resistor A. So it would be A, B, C, D, E, F. So the answer would be letter B. That's problem number 11. In problem 12, they ask us, two resistors A and B are connected in series, as you see here, in a circuit with a battery. The resistance of A is twice that of B, so A is equal to 2 times B. Which resistor dissipates more power? Alright, so let's start with A. A has a higher resistance, it's double that of B. So if we increase the resistance, what will that do? Well, that's inversely proportional to the current, so that's going to go ahead and decrease the current. And if we decrease the current, what will that do to the power? It will decrease the power. Alright, so they ask you which resistor dissipates more power. That will be definitely A. It has a higher resistance, which brings down the current, brings down the power. So your answer is resistor A. In the next problem, number 13 asks, the diameter of a wire A is greater than the diameter of wire B, but both lengths and resistivities are identical. For a given voltage difference across the ends, what is the relationship between the power of A and B and the dissipated power for wires A and B respectively? Alright, so we're going to go ahead and take a look at this one with different area. So everything is the same except for the area of the wire. So I'm going to go ahead and draw these two wires. So A is much larger than B. There we go. There we go. We're going to call this one A and this one B. Alright, so how does the diameter affect the resistance? Alright, so we're going to start there. Resistance is equal to resistivity multiplied times length over the area. Clearly wire A has a larger area, so let's just focus on wire A, what it does. If wire A has a larger area, so I'm going to put an arrow going up compared to B, then that means the resistance will be lower since they are inversely proportional to each other. Since the resistance is lower, and it will have a higher current since resistance and current are inversely proportional to each other. And therefore, if you have a higher current, we'll end up with higher power. So A, with the higher area, will have less resistance, more current, and therefore more power. Alright, so our answer would be letter C. PA is greater than PB. That is problem 13. Next is problem 14. Here we ask the following. Suppose your waffle iron is rated to 1 kilowatt when connected to 120 volt power source. What current does the waffle iron carry? Alright, so number one, we're going to find the I. What is the current? So we're going to go ahead and use this formula to solve for it. And part B, what is the resistance? So we're going to go ahead and use this formula to solve for the resistance. First of all, we're solving for the current, so I want to go ahead and isolate the I. So I'm going to divide both sides by the potential difference. So it's going to go ahead and give me I is equal to P over delta V. The power is in kilowatts, we want it in watts. So 1 kilowatt is the same as 1,000 watts. Divided by the voltage, which is 120 volts. So we go ahead and we divide both of those, the 1,000 divided by 120 gives us a current of 8.33 amperes. Alright, so that's part A. In part B, then they ask you what is the resistance. So we're going to go ahead and use this formula, isolate the R by dividing both sides by the I. So it's going to give us resistance is equal to the potential difference over the current. Alright, so potential difference was 120 volts. We're going to go ahead and divide it by 8.33 amps. So we get our answer, which is the resistance is 14.4 ohms. That is problem number 14. In problem 15, we're asked the following question. Light bulb A is marked for 25 watts for 120 volts, and light bulb B is marked for 100 watts for 120 volts. This means that each light bulb has its respective power delivered to it when it is connected to a constant 120 volt source. So for part A, find the resistance for each light bulb. So we're looking for R. We want to find the resistance. Alright, so we know the following. We are given the power in watts and we're given the potential difference. So we can go ahead and solve for the I and go ahead and plug it in here to solve for the resistance, which is what we're looking for. Alright, so let's go ahead and let's get rid of the I first. We're going to go ahead and do that. So it will look like this. I'm going to go ahead and divide both sides by delta V. So therefore I equals power over voltage. Now I'm going to substitute that here. So it will look like this. Voltage is equal to power over voltage times resistance. Now I want to modify this a little bit. I want to isolate the R. So I need to get rid of the P and the V. Alright, so I'm going to multiply both sides by delta V. So it cancels out, giving us the following. It's going to go ahead and look like this. V squared is equal to power times resistance. And now I'm going to go ahead and divide both sides by power. And there we go. Resistance is the potential difference squared divided by the power. Alright, and that is the formula we're going to go ahead and use. So let me rewrite it. Resistance is delta V squared over P. Erase the rest to give us ourselves plenty of space on the board. And let's see. For our first one, we have the voltage is 120. So this is going to be our numerator divided by the power, which was 25 watts. And that's going to be for light bulb A. And for light bulb B, it's going to look the same, 120 in the numerator, but the denominator is 100 watt bulb. Alright, so that is how we're going to get the resistance for each one of these. So it's going to be 120 squared divided by 25 gives me 576 ohms. And for light bulb B is going to be 120 squared divided by 100 gives us 144 ohms. Alright, that is part A of this problem. Part B, they ask you, during what time interval does 1 coulomb pass into light bulb A? So now we're going to focus on light bulb A only. So we know that the resistance of light bulb A, it is 576 ohms. We know its power, it is 25 watts. We know its potential difference, it is 120 volts. Alright, so those are all of our starting values, and we have a charge of 1 coulomb. So that will be Q 1 coulomb. Alright, so again, we're looking for the time interval. Alright, so here we go. We're gonna, our current is equal to the charge, which we have, over the time interval. Okay, so next, we also know that potential difference is equal to current multiplied times their resistance. Alright, so what I'm going to go ahead and do is move the R over here. And now see they're both equal I. So I'm going to equal them out to each other. So it's going to be delta V over R is equal to charge over time. Alright, now I want to go ahead and isolate the time. So I'm going to move it here to the numerator. And then, well, let's just cross multiply it. So it'll look like this. It's going to be delta V times delta T. And this is going to be delta Q times R. And again, I'm solving for time. So I'm going to go ahead and divide by delta V. Cancels out. So there's my formula. The charge multiplied times the resistance divided by the potential difference. That will give me the time it takes to get this charge across. Alright, so let's go ahead and plug in all the values. Time, therefore, is equal to the charge, 1 coulomb, multiplied times the resistance, 576 ohms, divided by the voltage, which was 120. So we'll plug those into the calculator, and we get our answer. 4.8 seconds. That would be the amount of time it would take to get that charge across the bulb. Alright, that takes care of problem number 15.
Next, we're going to go ahead and discuss resistors in series. 2 or more resistors connected end to end are said to be in series. So as you see in the diagram at the bottom, you have the battery connected to 2 light bulbs, and is where one wire ends, the other one begins, and that is in series. So those 2 light bulbs are connected in series. For the diagram in the middle, you have the resistors as the squiggly lines. You have R1 and R2. And to get the equivalent resistance, all you got to do when the resistors are in series is just add them together to get the total equivalent resistance. So when 2 resistors are connected to a battery, the current is the same for both resistors, because any charge that flows through the first resistor also has to flow through the second resistor. So they end up having the same current throughout all the resistors. The potential difference between A and B equals IR. The potential difference between B and C equals IR2. Therefore, the potential difference between A and C is equal to the following. So that would be delta V, which is the potential difference, is equal to the current times the first resistor plus the current times the second resistor. And if you factor out the current, it's just really current multiplied times resistor 1 plus resistor 2. So as you can see, the equivalent resistance, all you have to do is add up all of the resistors when they are connected in series. And equivalent resistors, K, Q, will have the same effect on the circuit according to Ohm's law. So again, to solve for the equivalent resistor, just add up each of the resistors, as many as you've got, add them together, and that will give you an equivalent resistor. The equivalent resistance of a series combination of resistors is the sum of the individual resistances, and is always greater than any individual resistance.
Next is example 5. In it, we're asked the following. It says 4 resistors are arranged in series. Find the equivalent resistance of the circuit. And part B says the current in the circuit if the closed circuit terminal voltage of the battery is 6 volts. And part C, calculate the electric potential at point A if the potential at the positive terminal is 6 volts. Now this question comes along with this diagram right here. So here they give us the resistance for each one, and as well as the 6 volts, and later on they're going to ask us about point A, that is between the first and second resistors. Alright, so let's go ahead and solve this problem. They're going to go ahead and ask us again, part A, find the equivalent resistance for the circuit. Alright, so for the equivalent resistance, that all we got to do is go ahead and add resistance 1 plus resistance 2 plus resistance 3, and so on. It continues. Alright, so going back to the diagram, we have 2 plus 4 plus 5 plus 7. So part A, it would just be as simple as just add them all together to get the equivalent resistance. Plus 4 ohms plus 5 ohms plus 7 ohms, that's 12, 16, 18 ohms total. That will be the equivalent resistance for part A. Notice that in the diagram next to it is already given. Alright, and in part B, it says the current in the circuit if the closed circuit terminal has a voltage of 6 volts. Alright, so now what we got to do there is we want to go ahead and find the current. We know that potential difference is equal to current multiplied times the resistance, and we have the equivalent resistance, and we have the voltage of 6 volts. So we're going to go ahead and use that to solve for the current. So the current's going to go ahead and be delta V over R. So 6 volt over a resistance of 18 ohms. So that's going to go ahead and give us the following. It is 0.333 amps. Alright, finally in part C, they ask you to calculate the electric potential at point A if the potential at the positive terminal is 6 volts. Alright, so where is point A exactly in our diagram? Again, it's right there, so it's gone through R1 only. So that's point A on our diagram. So again, only through the first resistor there. So to go ahead and solve for the electric potential, alright, so we're going to go ahead and use this formula. We have the current, and we're just going to put here R1. So it'll look like this. Potential difference is going to be the current, which is 0.333 amps, multiplied times R1, which is the first resistor, which had a 2 ohms resistance. So that will give you 0.667, and that will be in volts. So that will be the answer for part C. Alright, now let's go ahead and move along to our next problem. In problem number 16, they ask you, explain why the current in a real circuit very slowly decreases as time compared to its initial value. So what's happening to those charges? Why are they slowing? Well, it has to do with the friction with the atoms in the wire. As they collide with those atoms in the wire, that's going to go ahead and slow the current, slow the charges. So that's why it slowly decreases over time. Alright, next problem, number 16, they ask you as the following. It says a closed circuit consists of a battery with a terminal voltage of 12 volts. And the following resistors, 3 ohms, 6 ohms, 8 ohms, and 9 ohms. Resistors connected in series. Alright, so now that they're in series, it says with the battery at the bottom of the loop, positive terminal to the left, and the resistors in increasing orders, left to right, on the top of the loop. Calculate the equivalent resistance of the circuit. Alright, so let's go ahead and start with a quick drawing of it. Again, the voltage was 12, so I'm going to start with my battery. It's 12 volts. And let's put on there's 1, 2, 3, 4, and let's connect the circuit. Alright, and in order there were 3 ohms, 6 ohms, 8 ohms, and 9 ohms. Alright, so that is our setup. Positive currents going in that direction. Alright, so again, find the equivalent resistance. Since they are in series, all I have to do is add up the resistance of each one of these to get the equivalent resistance. So I'm going to go ahead and do that. So in part A, equivalent resistance is just simply 3 ohms plus 6 ohms plus 8 ohms plus 9 ohms. So it's going to give us 3 plus 6 is 9, 18, 26 ohms. That is the equivalent resistance for part A. Part B, the current. Alright, so for part B, will look like this. Alright, so we have our potential difference equal to the current times the resistance. we have the potential difference is 12 volts. So we're going to go ahead and isolate the I. So look at this, I is equal to potential difference over the resistance. So it is the voltage, 12 volts, over the R, 26 ohms. So that's going to go ahead and give us the following. That will be 12 over 26 gives us 0.46 amps. That is part B. That will be the current. All right, part C, they ask you the total power dissipated by the load resistors. All right, now that one, power is equal to potential difference square over resistance. So we're going to go ahead and use this formula to solve for the power. So it will be the voltage, which is 12 volts square over R. The resistance, the equivalent resistance was 26 ohms. So that's going to give us the following. That'll be 12 squared is 144 divided by 26 gives us 5.53. That's going to be watts. In part D, we're asked, what is the electric potential at a point between 6 ohms and 8 ohms resistor if the electric potential at the positive terminal is 12 volts? So we're looking between 6 and 8 at this point right here. So we're going to look for the potential difference first. So potential difference is going to be the current times the resistance. And the current, we had already figured it out, and it was 0.46. So we're going to go ahead and plug that in, 0.46 amps. And we're going to go ahead and multiply that times the equivalent resistance to this point. So that'll be 3 plus 6, that'll be 9 ohms. So that goes ahead and gives us the following. It's going to be 9 times 0.46 gives us 4.1. That's going to be volts. All right, so now we started with 12, so we've lost 4.1, so it will be this 12 volts minus 4.1. It's going to go ahead and give us about 7.9 volts, and that will be the answer for part D. In problem 18, we're asked the following question. It says, the current is measured with an ammeter at the bottom of the circuit. When the switch is open, does the reading of the ammeter increase, decrease, or not change? All right, so let's look at our diagram right here. So here we have our battery, and we have 2 resistors and the switch. Now here the current is going to go in this direction through the first resistor, and if the switch is closed, like it is right now, it's going to go ahead and take the lowest path of resistance, so they can go through here and completely avoid resistor 1. Now, they're saying if we open the switch, so now it's no longer connected, the current's going to have to go through resistor 1, and now it's going to be forced to go through resistor 2. So they're saying what will happen to the reading in the ammeter if we open the switch? So now the current will have to go through both of them, so therefore the equivalent resistance will be adding R1 plus R2, so the resistance overall is going to go ahead and increase as we're adding more. So if we increase the resistance, that is inversely proportional to the current, so that will decrease the current. So therefore, the answer for this problem will be letter B. It will decrease the current overall. Now, in problem 19, they ask you, the circuit consists of 2 resistors, the switch, an ammeter, and a battery. When the switch is closed, the power, C, so C for close, is delivered to resistor 1. When the switch is open, the following statement is true about, which of the following statements is true about PO when the power is open and delivered to R1. So here's our diagram, very much the same one, and the current's going through here. So let's talk about power. What happens to the power once you open it? Now the current has to go through both resistors. Once it's open, it has to go through both resistors. So therefore that increases the resistance. If we increase the resistance, that will decrease the power. Alright, so they are inversely proportional, so higher resistance equals less power. So less power when it's open, so therefore the solution for this one will be A. PO, power when it's open, is less than the power when it's closed. That is the answer for this problem. This brings us to the end of our week 31 lesson. Thank you so much for watching.